Hi and welcome to a brand new video tutorial, and today we're going to be covering JC A-Level Physics Chapter 1, which is Physical Quantities, or more specifically measurements, right? And this one is a bit different from the one that you learn in O-Levels in the sense that over here, there are a few different extra sections, right? Homogeneity, uncertainty, and vector addition, right? Especially this one, important one. Vector addition is a very, very important fundamental concept in JC physics. Even though this is the first chapter, it's a bit more basic, but it's a very important base for the rest of the chapters, right? So if you don't know me yet, I'm Jing from the A1 Physics. I specialize in helping secondary and JC physics students. And yeah, let's jump straight into the tutorial. Now, first I'm gonna do a recap of what we learned in O-Levels, right? Base quantities are basically the most basic form of units. So for example, mass, length, right? All these units are the smallest form of units already. You cannot break it down into even smaller units. So, all these are the 6 base quantities that you gotta memorize for physics, and over here are the 6 SI base units for these base quantities. Right, derived quantities are basically quantities that are derived from a combination of base quantities. So for example, force. The unit for force we know is Newton, right? So we say that the derived unit is Newton. But actually we know that force is just F equals to ma, right? The unit for mass is kg, and the unit for acceleration is meter per second square. By the way, in JC physics, instead of doing meter per second square, you want to just put s minus 2. Like, you don't want to put the slash anymore, right? Because there's going to be a bunch of many units, and so it's much more cleaner to just put the minus instead of the slash, right? So force, the unit that is derived, that we write, is Newton, but if we were to break it down to its base units, it's basically kg ms minus 2, right? So the basic quantities are kg, meter, second, and the derived quantity is just force, which the unit is Newton. Right, now let's talk about homogeneity of equations. Now, the basic rule for physics is that both sides of the equation must have the same units, right? So for example, it doesn't make sense to add 5 kg plus 5 newtons. It doesn't make sense to add a kg to a force. Or for example, it doesn't make sense to add 5 seconds plus 5 meters. Like, it just doesn't make sense, right? An equation must always have the same units so that two things can be added or subtracted from each other. So when you want to add quantities, we got to make sure that it's, for example, 5 meters plus 5 meters equals to 10 meters, right? Basically, the rule is that every quantity that is separated by a plus must have the same units, and all the quantities on the left and right side of the equal sign must have the same units. That's how it makes sense to add these things together, right? So that's the concept of homogeneity, which says that an equation must have the same units. So let's look at this question from a few years ago, and let's try to apply the concept of homogeneity. Now over here we have the expression C equals to AT plus BT cubed. And we know that the units for C is Q over change in temperature, right? So the units for C is actually, unit for Q is energy, which is joules, and unit for temperature is Kelvin, right? So the unit for C is joules over Kelvin, which is joules Kelvin minus 1. So we know that over here in this equation, in fact, let me just expand this equation over here. C equals to alpha T plus beta T cubed. This guy, we know the unit is JK minus 1. So we know that every single term in the equation must also have the same unit, jk minus 1, right? That's the concept of homogeneity. So let's zoom in over here, alpha T. We know that the unit for temperature is Kelvin, right? Unit for temperature is Kelvin. And so if we want to make this entire term into J Kelvin minus 1, then we know that the unit for alpha gotta be J Kelvin minus 2, right? Because J Kelvin minus 2 times Kelvin gives us the final result that we want, which is J Kelvin minus 1. Right, so let's just do another example for beta. Over here we have beta T cubed equals to J Kelvin minus 1. So the unit for temperature we know is Kelvin cubed. So the unit for beta gotta be J Kelvin minus 4. Right, because J Kelvin minus 4 times Kelvin cubed equals to J Kelvin minus 1. That's why the answer for this question is D. Right, so that's how we solve these questions using the concept of homogeneity. Okay, so this one is just an important side note. All physically correct equations are homogeneous, but not all homogeneous equations are physically correct, right? So what does this actually mean? Basically, for example, the equation kinetic energy, Ke equals to half mv squared. Right, it makes sense because if you break down the units, basically both sides have the same units, which is joules. But for example, if you write an equation like Ke equals to 3mv squared, right? Obviously this formula is not correct because we know that Ke must be equals to half mv squared, even though this equation is technically homogeneous. Like both sides have the same unit, which is joules, but it still doesn't make the equation physically correct, right? Because we know that in the real world, kinetic energy is half mv squared. So that's what it means by all physically correct equations are homogeneous, but not all homogeneous equations are considered to be physically correct. So this one is just a side note for you to take note of. Right, so over here are a list of prefixes that are tested in A-level physics. Right, I think the only difference with O-level physics is this extra addition of pico. Right, so what are prefixes? Basically, if I say something is 1 kilogram, because kilo has a power of 3, we say that 1 kilogram equals to 1 times 10 to the power of 3 grams equals to 1000 grams. Right, you just add the prefix behind the number. Now let's talk about the idea of uncertainty. Right, the basic idea with uncertainty is that we cannot be truly sure about the value that we measure. Right, we can't be sure that it's the actual true value of the quantity. So for example, if we have a piece of something over here and we use a meter rule to measure this thing, and we realize that this thing lies somewhere in between 3.5 and 3.6, right? It's somewhere in between. Due to the limitations of the instrument, we cannot be 100% precise in our measurement. So what we do is we just say that this guy is 3.5 cm plus minus 0.1 cm, right? Because we are uncertain about whether this guy actually is 3.5 or 3.6. So we add this uncertainty over here, which is 0.1 cm, right? But we know that for sure the quantity must be between the range of 0.1 cm because the ruler can measure up to 0.1 cm, right? There's no way this guy can be like 3.7 cm. So this uncertainty is kind of the maximum bounds of range that the value can take, right? So for example, if we measure a pencil using a meter rule and we found out that the length of the pencil is 14.6 cm is the measured value and 0.1 cm is the actual uncertainty of the pencil. So actual uncertainty, we represent it by this symbol over here, which is delta x. Now we're going to learn this term called fractional uncertainty, which is basically the actual uncertainty over the measured value. For this pencil over here, the fractional uncertainty will be delta x over x, which is just 0.1 over 14.6, right? That's called the fractional uncertainty. The percentage uncertainty is basically the same thing as the fractional uncertainty. It's just that you times the thing by 100%, right? So this guy, the percentage uncertainty will be times 100% equals to 0.68%. So this one is the percentage uncertainty, right? So I'm going to give you some examples about how to solve uncertainty questions. But before that, let me just go through some rules for uncertainties. So for the significant figures, you want to make sure that your uncertainties are expressed in 1SF, right? So for example, over here, the actual uncertainty plus minus 0.1, this is always in 1SF. And the quantity will then be expressed to the same dp as the uncertainty. Right over here, because the uncertainty is in 1 dp, then the quantity is also in 1 dp. So the quantity follows the dp of the uncertainty, and the uncertainty is always 1SF. So that's the rule. Right, so let me just give another quick example. If my uncertainty is, plus minus 0.005, right, we want to express it into 1SF. We want to make sure that our value is expressed in terms of 3 dp. So our value might be 67.123, right? Our value wants to follow the same dp as the uncertainty. Okay, so let's go through some rules for adding uncertainties. Right, this table is going to make a lot more sense when we try the examples later, but let me just run through this table first. So the idea is that if you plus or minus two different values, what you want to do is you want to add the individual uncertainties of every single value, right? And also, you want to keep the factor. So if it's, 3x plus 2y, the uncertainty of x gotta be 3 times the uncertainty of x. The uncertainty of y gotta be 2 times the uncertainty of y, right? So addition and subtraction, both of the cases, you want to plus the uncertainties together. Now for multiplication and division, what you want to do is you want to add their fractional uncertainties. So the fractional uncertainty of the value is equal to the addition of the individual fractional uncertainties, right? Okay, again, this is going to make a lot more sense in the examples later, but it is what it is. And also, one more thing is that you notice that for times and divide, we don't care about the factors, right? If it's ax plus by, we just ignore the factors in the calculation of the fractional uncertainties. Yeah, so the factors do not affect the fractional uncertainties at all, right? So we notice that addition and subtraction, they both follow the same rules. Multiplication and division, they also both follow the same rules. Now, the last thing I want to go through is multiplication and division with powers, right? What if it's ax to the power of m? So as usual, we want to ignore the a and b, right? We ignore the factors when talking about multiplication and division. But for the powers, we gotta carry it over and times the fractional uncertainty by the power, right? And again, it's both the same case for multiplication and division, right? So now let's try some exercises on uncertainty, right? So over here, we have a question on uncertainty. So feel free to pause the video and try the question yourself first, right? So the idea over here is that we want to find the diameter of a single steel ball over here. Now, how do we find the diameter of 4 steel balls? Let's call the diameter of 4 steel balls d. The diameter of 4 steel balls is given by y minus x. Y minus x gives us the diameter of these 4 steel balls. So the diameter of one single steel ball is actually, let's call it small d, is actually y minus x divided by 4, right? Which we can rewrite into 1/4 y minus 1/4 x. So we know that over here, this is a case of actually the first scenario, which is addition and subtraction, right? And if you remember the rules for addition and subtraction, if you want to find the uncertainty for small d, we gotta take 1/4 times the uncertainty of y plus 1/4 times the uncertainty of x, right? In fact, let me just scroll back to the rules over here, right? Over here, we gotta take the individual uncertainties plus together and times it by the factor that, you know, the value is multiplied by. Okay, so both addition and subtraction, you want to add the individual uncertainties together multiplied by the factor, right? So this will give us 1/4 times 0.1 plus 1/4 times 0.1 equals to plus minus 0.05 cm. And that's the uncertainty in this question. But over here, we gotta find the diameter together with its associated uncertainty. So to find the diameter of one steel ball, we just look at these values. We don't care about the uncertainty, right? So it'll be diameter equals to y minus x. That will give us 4 steel balls. So we gotta divide it by 4, right? You just want to calculate it normally, ignoring the uncertainties. So it'll be 4.0 minus 1.0 over 4 equals to 0.75 cm, right? So we notice over here that this one is the actual diameter and this one is the uncertainty of the diameter. So if you have to express the whole thing, it will be diameter equals to 0.75 plus minus 0.05 cm, right? That's the diameter expressed together with the uncertainty. So as usual, we notice that our uncertainty is in 2dp, so our actual value, we gotta leave it in 2dp as well, right? So that's just a basic example on uncertainty, right? So we have a more standard type of question for uncertainty. So feel free to pause the video and try the question out yourself, right? So over here, we want to find the value of g and its uncertainty. Now let me tell you the wrong way that students might do this question first, right? First of all, we notice that over here is a square root, which is basically saying the same as 2 pi L to the power of half over G to the power of half, right? Square root is just, you know, the individual things to the power of half. Now, the rule that we are following is this rule over here, right? Something equals to something times something to the power of something. Now, let me tell you the wrong way that students might do this. They might say that fractional uncertainty of T equals to half times the fractional uncertainty of L plus half times the fractional uncertainty of G. And if they want to find the uncertainty of G, what students might do is they might try to rearrange this equation and say that, you know, bringing this to the other side, it'll be uncertainty of T minus half over uncertainty of L equals to half times uncertainty of G. Then they try to solve for the uncertainty of G, right? But this will be wrong. So the key to solve these questions involving uncertainty is to always make the one that you want to find as the subject of the equation, right? So let me show you the correct way to do this question. What we want to do is we want to make G the subject of this entire equation. So over here we'll get G equals to 2 pi square times L over T square, right? That's what we want to do. We want to make G the equation, and now we want to form our fractional uncertainty entire line. So now we'll get fractional uncertainty of G equals to, we ignore this guy, so it'll be fractional uncertainty of L over L plus 2 times fractional uncertainty of t, right? And as you can see over here, this one is actually different from this. So we always got to make the one that we want to find as the subject of the equation first. But before we solve this equation, we first got to find what is the measured value of g, right? So to find the measured value of g, we just want to ignore the uncertainties, similar to the last question. When we want to find the actual value of the diameter, we just ignore the uncertainties and we just focus on these values. So simply what we do is we just sub the values inside. We have g equals to 2 pi square times L. So the value of L, we just ignore the uncertainty. We take the measured value of L, which will be 1.150 over t squared. So t, the measured value is 2.16, equals to 9.73, right? And of course, we got to make sure that we include the units every single time. So over here, the units of g is L over t squared, right? So L, the unit is meters, and time, the unit is second. So over here is the unit of g will be meter second minus 2, right? Since it's over L square. Okay, so now this one is the actual value of g. So how do we find the uncertainty of g? We sub this actual value inside our uncertainty equation. So now it will be uncertainty of g over 9.73 equals to fractional uncertainty of L, which is 0.005 over 1.150 plus 2 times the fractional uncertainty of t, right? Which is 0.01 over 2.16. And if we solve this equation for delta g, we will get 0.1, right? Remember that we want to leave the uncertainty in 1SF. So we got to leave this in 1SF, right? So the value of g together with its uncertainty will be g equals to 9.7. Now our uncertainty is in 1 dp, right? So our actual measured value got to follow the same dp as this. So we want to leave it in 1 dp over here as the final answer. So it would be 9.7 plus minus 0.1 whole thing meters per second square. Right, and that's how to solve uncertainty questions. Now, for more complicated functions, there's actually another method which is called the first principle method. And it's actually quite important. So let's go through this first principle method. The intuition behind this is, imagine we have two different sticks, right? And we want to find what's the total length of the two sticks together with its uncertainty. So like this one's L, this one's L, and let's say we want to find the length of 2L. The idea is that imagine both of the sticks are at their minimum values. You know, both guys have an uncertainty of 1 cm. So minimally both guys will be 4 cm plus 4 cm equals to, 8 cm, right? That's the minimum length. Now let's assume that both of these guys, they are at the maximum values. So this guy is 6 cm and this guy is 6 cm, and the maximum of these two values is 12. Right, we can say that over here, the range of the total length of these two guys can only fall between 8 and 12. It cannot be less than 8 or it cannot be more than 12, right? Because 8 is already the minimum and 12 is already the maximum. So that's the intuition behind the first principle method. We'll get an answer like 10 plus minus 2 cm, right? Because over here, smaller than 8 or it cannot be bigger than 12. So what we want to do in the first principle method is we want to find the maximum value, we want to find the minimum value, and we want to minus the two values. So Z max over here will be 12 cm and Z min over here will be 8 cm, and to find the uncertainty, we just take 12 minus 8 times half, which is plus minus 2 cm, right? So that's how we find the uncertainty using the first principle method. We just find the minimum and the maximum value and we halve the difference between them, right? So a perfect example for the first principle method is this kind of questions over here. So over here is 1 over u plus 1 over v equals to 1 over f. It's a very kind of complicated function, right? We can't just use the rules that we learned just now. We gotta use the first principle method, right? So first, let's assume that u is the biggest value and v is also the maximum value. So the maximum value of u will be 53, right? Because 50 plus 3 millimeters. Maximum value of u will be 205. So using this assumption, we'll get 1 over 53 plus 1 over 205 equals to 1 over focal length. And if we solve this equation, we'll get focal length equals to 42.1 millimeters. Right, this one is the maximum value of the focal length. Let's take the minimum possible value. So the minimum value of u will be 47, right? 50 minus 3. And the minimum value of v will be 195. So now the minimum value of f will be 1 over 47 plus 1 over 195 equals to 1 over f. And if we solve this equation, we will get 37.9 millimeters. Right, so if you want to find the uncertainty of f, we just gotta take the maximum value, which is 42.1, minus the minimum value, and we halve the whole thing, and that will give us plus minus 2.1 millimeters. Right, so that's how we use the first principle method. It's basically just finding the in between the maximum and the minimum value. Right, now let's talk about systematic versus random errors. Right, so systematic errors are basically errors that are where all the readings are more or less than the true value. So a very simple example for this is, a piece of wood that is 5 cm long, right? The wood is actually 5 cm long. And let's say we use a ruler to measure this wood. So the ruler, let's say this is a proper ruler from 0 to 5, so the ruler will read 5 cm, right? Now let's say the ruler has a systematic error. Let's say the ruler starts at 2 cm instead of 0 cm, and so the ruler will measure this piece of wood to be 7 cm instead, right? So we call that a systematic error. It's because every single time this ruler measures something, it will always be 2 cm more than the actual value, right? Due to this systematic error of 2. So systematic errors can be eliminated. You just want to, remove the error and replace it with a proper equipment. And the most common example is the zero error, right, in vernier calipers and micrometer screw gauge. Now, random errors, on the other hand, are errors that are scattered around the true value. So sometimes it's more than a true value, sometimes it is less than a true value, right? And a very simple example of this is human error. So for example, over here, we are trying to time the period of a pendulum. We have a stopwatch over here, and we're trying to time the period of the pendulum oscillating left and right 1 full cycle. So due to our human reaction time, right, sometimes we press the stopwatch a bit earlier than the actual time. So it can be a mix of like more than the actual value and less than the actual value. And so we call these errors random errors. And the thing about random errors is that they cannot be eliminated, right? You cannot eliminate human error. There's always going to be some degree of error. You cannot perfectly time the stopwatch at the exact moment the pendulum comes back. But random errors can be reduced by averaging. So you can take the timing of 20 oscillations and, divide it by 20 to find the average of one oscillation. That's one way to reduce random error, but you cannot eliminate it completely. As opposed to systematic errors, you can eliminate it completely. Right, so that's the difference between systematic and random errors. So very closely linked is this idea called accuracy versus precision, where accuracy is basically how close the readings are to the true value, and precision is how close the readings are together. So let's say over here we have this archery thing over here. Right, we imagine the bull's eye to be the truth of the value. So if all the readings are close to the true value and they are close to each other, we say that it's accurate and precise. On average, they are close to the true value, but the readings are scattered everywhere. We say that it's accurate but not precise, right? If the readings are very close together, but they are far away from the actual value, right? They're close together, but they are far away from the actual value, we say that it's not accurate, right? Because it's not close to the actual value, but it is precise because the readings are grouped together. Finally, if the readings are nowhere near the true value, nor are they close together, we say that it is not accurate and not precise. Right, so accuracy is affected by systematic error, whereas precision is affected by random error. Right, now let's cover adding vectors. This one is the most fundamental part for JC physics, right? And we're going to recap what we learned in secondary school, which is how to add vectors using the tip to tail method. So example over here, we have two different vectors, A and B. We want to add these two vectors to find the resultant of the two vectors. How we're going to do it is we're going to take the first vector, put it over here, and we're going to connect the second vector to the end, right, like a snake. Once we've connected all the vectors like a snake, right, we draw a line from the start pointing to the end, and this is the resultant of the two vectors. Right, so that's just a quick recap of how to add two vectors using the tip to tail method. Now, the thing we're going to learn here is how do we subtract vectors? How do we take A minus B, right? And actually, the way to do this is quite simple. Is you just want to take A plus negative B, right? Because it's the same thing as A minus B. And how do we find negative B? Is basically the inverse of B, right? So if positive B is this way, then negative B is just B flipped around the other way, right? So what we want to do is, if we want to take A minus B, we first flip the positive B around to negative B, and then we plus them together like normal vector addition, right? So now we just take A plus minus B, then we draw a line from the start to the end, and that gives us our resultant vector. So subtracting vectors, just go and flip the vector around, and you want to plus the negative version of the vector. Now here comes the really important part for physics, resolving vectors. Let's say we have 5 Newton's force over here, and this force is actually 30 degrees to the horizontal. So the thing we can do about this force is we can actually resolve this force into the horizontal and the vertical components. Now what do I mean over here? We can break down this diagonal force into a horizontal component and a vertical component. Now how do we find the values of the horizontal and the vertical components. Now we gotta use a bit of trigo. Now we know that sine 30 gives us the opposite over the hypotenuse, right? Sine 30 equals to opposite over hypotenuse. So it'll be this guy over this guy. So it'll be opposite over hypotenuse, right? That's what sine 30 gives us. So by making opposite the subject, we can see that opposite equals to hypotenuse times sine 30, right? And our hypotenuse, we know that the value of our hypotenuse is actually 5 newtons. So we can say that opposite equals to 5 sine 30, right? Meaning that this vertical component has actually the magnitude of 5 sine 30. That's how we resolve the vertical component of the force. Now we can do the same thing for the horizontal component of the force, right? We can say that cosine 30 equals to adjacent, which is this one is our adjacent, over the hypotenuse, right? Cosine equals to adjacent over hypotenuse. So now we can find the value of adjacent using adjacent equals to hypotenuse times cos 30 equals to 5, right? Cos the hypotenuse is 5 times cos 30. So this horizontal component over here is actually 5 cos 30, right? So that's how we actually break down this 5 newtons force into its horizontal and vertical components, right? So you don't actually have to do this trigo thing every single time. Eventually, as time passes, you'll get used to seeing that the side that the angle touches is cosine and the side that the angle doesn't touch is sine, right? But you're just gonna get used to this over time. Just now, I was just trying to teach you the derivation of cosine and sine. Right, so actually, why do we learn to resolve vectors? It's actually because it allows us to add vectors easily. And I'm gonna show you with this example over here. So over here, I'm just going to give you a very, very simplified example using fake numbers just to drive the point. Then we'll do a real example later, right? So imagine we have two different forces over here and we want to find what's the value of the resultant of these two forces. So what I'm going to do is I'm going to resolve these forces into the horizontal and the vertical components. Right, let's say this guy, the horizontal component is, 4 newtons, and this guy, the vertical component is, let's say it's 3 newtons. Let's say this guy, the horizontal component is 1.5 newtons, right? Again, I'm just using like fake numbers just to explain the point. And over here, the vertical is like 1 newton, right? If you want to add these two forces together, we can just add the horizontal and vertical components separately, and then we combine together at the end. So let's add the horizontal components. We have 4 newtons plus 1.5 newtons, right? So the horizontal components plus together will give us 5.5 newtons to the right. So now we want to add the vertical components together. Now we have 3 newtons upwards and 1 newton downwards, right? So the total resultant of the vertical component is just 2 newtons upwards, since the 1 newton cancels out the 3 newton. So now overall, we have a resultant of 5 newtons horizontally, 5.5, and a resultant of 2 newtons vertically. And so what we can do is we can actually plus the horizontal and vertical components together, and we realize that we can actually use Pythagoras theorem to find the value of this resultant force, right? In this case, it'll be 5.5 squared plus 2 squared equals to r squared. Right, so in this case, the resultant force will actually be 5.85 newtons. Right, so that's the point of resolving the forces. We can add the horizontal and vertical components only. So now let's do a more realistic example over here. We have, now we know the angles in between the horizontals. Right, so if I were to resolve this guy into the horizontal component, it will be 5 cos 40. And the vertical component will be 5 sine 40. Right, this guy in the horizontal component will be 3 cos 15, and the vertical component of this guy will be 3 sine 15. Right, so the horizontal components plus together will be 5 cos 40 plus 3 cosine 15, right? That's the resultant of the horizontal component. And the vertical component plus together will be 5 sine 40 minus 3 sine 15, right? Minus because this guy is going up and this guy is going down. And so now we can use Pythagoras theorem to actually find what is the value of this resultant force over here, right? This resultant force will just be this square plus this square equals to r square. And now we can calculate r to be 7.16 newtons. So that's really the beauty of resolving forces into horizontal and vertical components. Right, so let's just do one more exercise over here. Let's say we want to find the resultant of these three forces, and we also want to find the angle of the resultant force. right? So first, let's resolve the forces into the components. Over here, this guy can be resolved into 35 cos 45 horizontally, and vertically this guy will be 35 sine 45, right? As for this guy, it will be 15 cos 30 horizontally, and vertically this guy will be 15 sine 30, right? This guy doesn't have a horizontal component, it just has a vertical component. So now let's plus all the vertical components together. Vertical components plus together will be 78 minus 35 sine 45 minus 15 sine 30. Right, that's for the vertical component. For the horizontal component, it will be 35 cos 45 minus 15 cos 30. Right, that gives us the horizontal component. So now let me just quickly evaluate these two sums. So this guy actually equals to 45.8 and this guy actually equals to 11.8. Right, so we know that our resultant vector looks like this. It is 45.8 downwards and also 11.8 to the left, right? So our resultant vector is this guy over here. And very easily, we can use Pythagoras to find the resultant vector, right? We'll take 11.8 square plus 45.8 square equals to r square, and we'll get r equals to 47.3, right? So that's the final answer. R equals to 47.3. Right, so that's the magnitude of r. So now let's just try to find the value of this angle over here, the angle that r makes to the horizontal. Right, so over here we'll take tangent theta equals to opposite over adjacent, so it will be 45.8 over 11.8. So theta equals to tangent inverse the whole thing, which will give us 75.6 degrees. Right, so that's how we just use basic trigo to find the angle. Right, so that's the full guide to the first chapter of JC1, and really the most important part for this chapter, especially for the next few chapters, is to learn how to resolve your forces. Right, so as usual, I'm Ting from the A1 Physics. If you want to join my JC Physics tuition, just go and WhatsApp the number somewhere around the screen and I'll send over to you more details about the tuition. Alright, see you in the next video.